Okay. So the next test, the next midterm that y'all have is coming up on Wednesday. So my plan was to follow a very similar format. So I'm going to write an hour test, and then you'll have, if you're in a time zone that's close to our time zone, then you should take it at the standard class time, that is from 11:30 to 12:30, more or less. And once again, I'll proctor it over Zoom. So essentially the mechanics of taking the exam should be the same as last time. Again, send me an email if you're in a time zone that's very far from Eastern time zone, so that I can make a test that's available on Sakai for a longer period of time. You also will have 24 hours, a 24-hour window within which you can take the test. Once again, it'll be a 1-hour test. Those of you who are not in a nearby time zone should take a video of yourself taking the test and then try to compress it. There were some issues with sending large video files before, so if you could try to compress the video, that might help things out. Any questions just on the kind of format or the mechanics of the test?
I'll just say you can choose to record the video to like a Zoom cloud, and then it gives you a link afterwards and like an easier way to share with you.
That's also a good tip. Thank you. My intention for what we should cover is as follows. So today we're going to essentially finish our work in chapter 3. So the main focus is chapter 3, which is second order linear differential equations. So this is going to first include the first chunk, which is like 3.2 existence uniqueness theorems on intervals, and details about how these existence and uniqueness theorems kind of play out. Also Wronskians. Of course, Wronskians are very important in determining when you have a fundamental system of solutions. So definitely expect these to be on the exam. You definitely need to be able to solve all homogeneous second order linear with constant coefficients. Quickly. I would say it's not enough just to be able to solve homogeneous second order linear with constant coefficients, but these should be like down pat, so to speak. So remember, there are 3 cases corresponding to the characteristic polynomial. What are the 3 cases that we need to consider?
2 distinct real roots, a real repeated root, and complex conjugates. That's
right. 2 distinct real roots, 1 repeated real root, or complex conjugates. So you need to be able to kind of quickly extract solutions from this stuff. You should also be familiar with changes of coordinates, or kind of the Euler equations. And then the next part is when we add back in, so non-homogeneous second order linear differential equations. So what are the two methods that we kind of have for, or what's the main idea that we have for solving a non-homogeneous second-order differential equation?
We find the solution to the homogeneous, like the um, relevant homogeneous equation, and then we find a single solution to the non-homogeneous.
That's right. So general solution looks like C1 y1 plus C2 y2 plus y, where this chunk is the general solution to the homogeneous piece, and y is a particular solution to the non-homogeneous differential equation. And we have two different methods for finding a particular solution, and what are they?
Undetermined coefficients,
Undetermined coefficients.
and then variation of parameter.
Yep. So undetermined coefficients essentially asks you to guess. And this is a viable technique when g of t is a polynomial or a cosine or sine function or an exponential function, and then variation of parameters. Otherwise. And then I hope to be able to put the following things on the test, maybe just a little bit, which you haven't seen yet, which are nth order homogeneous differential equations. Nth order linear. Now, we haven't covered this topic yet. This is what we start seeing in chapter 4. I want to make kind of some comments. First of all, we should get here today. I plan on starting to discuss some of this material today, in particular, some of the existence and uniqueness theorems around this. And the second comment is that, well, there are 3 comments. The second comment is that morally, once you understand second order linear, then you really understand nth order linear homogeneous differential equations. So as we'll see in a rather brief amount of time, the nth order linear homogeneous differential equations that we have any hope of solving are precisely those where the coefficients are constants, and then it just boils down to a characteristic polynomial sort of argument where your solutions will look like e to the roots of the characteristic polynomial. So essentially in the same way that second order linear constant coefficient differential equations were essentially totally determined by their characteristic polynomial, the same phenomenon appears for higher order linear homogeneous constant coefficient differential equations.
Can you take the Wronskian of multiple, like?
Yep. Yes, exactly. And we should get to that today. So there's a perfectly reasonable definition of a Wronskian. We'll get into definitions of linear independence of solutions. And then the last comment that I want to make is that we won't really be spending much time in chapter 4. We'll really only do 2 sections. And we're not going to spend a lot of time in chapter 4. What I want to do today is do some material, finish up chapter 3, introduce us to chapter 4, and then I want to honestly finish my material in chapter 4 by Monday. So a very, very brief discussion of these nth order linear homogeneous differential equations, because I want to spend what time we have left, namely Tuesday, Thursday, Friday, and Monday, on systems of differential equations, which introduces more linear algebra into the math. So I just want to let you know that some of the easier problems, maybe some problems that we discussed today about nth order linear homogeneous differential equations, might be fair game for me to ask on the test. Any questions about this this kind of plan or this description?
Looks like someone asked about order of reduction in the chat.
Oh, reduction of order. So
Yeah, sorry.
3.8 we will not discuss. So 3.8 is right out. 3.7 is what we're discussing today. So 3.7, the thing about 3.7 is that 3.7 is like applications. So there's some interesting material, in particular some physics-related material that we'll discuss today and that we started discussing yesterday about mass spring systems. But I would say that you shouldn't focus on 3.7 because the main mathematical tool that is used in 3.7 is all the previous parts of chapter 3. In particular, in 3.7, we're just kind of exploring deeper the solutions to differential equations that we already know how to solve. So I would focus on 3.1 through 3.6 mostly, if you're going to spend your time studying. But yes, reduction of order is something that I forgot to mention. Reduction of order is fair game. Thank you for that question. Okay. Any other questions? Okay. So let's go back to what we were discussing last time, unless there are any other questions, which I didn't hear. Okay. So last time we were discussing mass spring systems. So these are just one place out of many, many places in physics where second order non-homogeneous differential equations govern the physics of the problem. And I mentioned some of the things last time, but essentially all oscillatory motion, harmonic oscillators, vibrating strings, masses on springs, and the electrical current in a circuit, all of these are described by these differential equations that we now know how to solve. So in particular, what we kind of derived or discussed last time was the following. You have some spring and a mass m that is pulling the spring down. So there's some rest length of the spring mass system where nothing is moving. And we call the length of the spring at rest L. And then we're interested in what happens if we disturb the mass spring system, which should be like either pulling or pushing on the mass, either up or down. So here, we're going to measure the distance between the rest length of the spring and the length of the spring as a function of time by u of t. So here, say, if I have moved the mass down from its rest length by 1 inch at time t is equal to 0, then u of 0 will be 1. That's how we're measuring u of t. What we did is we used Newton's laws to write down a differential equation which the motion must satisfy. The motion here means the function u of t. So this kind of goes back to the idea that I discussed at the very beginning of class, that somehow Newton's laws, well, Newton's laws in physics, but other laws in biology and chemistry and economics and things like that, make it so that writing down a differential equation is supposed to be the easy part. And solving it is supposed to be what is the difficult thing, more or less. At least this from a certain perspective. So what we wrote down yesterday was we got, so we're using force is equal to mass times acceleration. So m times the acceleration associated to the object, if the position function is u of t, is u double prime of t. And this is going to be equal to the forces by Newton's law, F is equal to ma. Well, the forces are the force of gravity acting down minus the force of the spring, L plus u of t. So here, k is some constant which tells you how springy the spring is, and L plus mu of t is some quantity which tells you how far you are deviating from the rest position of the mass on the spring. And then possibly we're going to have a force of, what is this called? What did I call this last time?
Damping?
Damping, yes, thank you. Damping force, and then possibly F sub, I'll call it F, for this is like forcing. So damping is something that should be kind of slowing down the whole spring system, and forcing should be some additional function that you can write on this side that would make this a non-homogeneous differential equation. Either of these terms would make this a non-homogeneous differential equation, and these would affect the overall equation of motion. So if we're working with an ideal spring, we're going to pretend that there's no damping and there's no forcing, so we set these two to 0, and we end up with the differential equation m u double prime of t is equal to negative KL. Remember, no, not, it should be negative K u of t. Remember that mg minus KL vanishes by our examination of the free body diagram, or by our examination of the mass at rest. And we can rewrite this as a homogeneous second order linear differential equation. Mu double prime of t plus Ku of t is equal to 0. I know that I'm doing some review, but does anyone have any questions at this point about what I've done?
No.
Okay. So the characteristic equation is mx squared plus k is equal to 0. And we solve this by getting plus or minus square root of negative 4 mk all over 2m. And we found that the roots then are equal to plus or minus square root of k over m. So what is the general solution to this equation of motion? Oh, sorry, there's an I here. I have complex conjugate roots.
Cosine k of n, k over n plus sine root k over n.
Yep. A cosine of root k over m t plus b sine of root k over m times t. And the thing that we want to kind of discuss is we want to explore this equation further, because despite the fact that we've found a general solution, there's actually still a lot that we can find out about this equation. So this is this. Okay. So as I mentioned the last time, First of all, we know what the period of this oscillatory motion is. The period, so also as a notation, we're going to write k over m is equal to omega 0. So this is going to be some constant that is determining some important fact about this system. So first of all, the period of motion is what?
2 pi over omega 0.
Yeah, 2 pi over omega 0, which is the same thing as 2 pi times root m over k. One way to see this is to notice that both cosine and sine are periodic with period 2 pi. So the question is, what is the increment in time that you have to step forward such that this argument and this argument both step forward by 2 pi? So really what we're solving is, when is root k over m times t equal to 2 pi? That's exactly this. Okay. So this is about what we got to last time. Before I begin anything new, is this all right? Okay. Everyone is being a little quiet on this question, which is fine. So we're going to make an interesting change of coordinates, or we're going to rewrite this family in an interesting way that will maybe elucidate what is actually happening with this family. Okay, so the first question is, does anyone remember the addition formulas for sine or cosine off the top of their heads? If the answer is no, that's totally fine.
No, not at all, to be honest.
Not at all. Okay, so what I'm going to remark in the following thing is, you never need to memorize addition formulas, addition trig formulas again. So what I'm about to show you is a helpful way to derive the addition formulas for trig functions using Euler's formula. So the only thing you need to remember is e to the I t is equal to cosine of t plus I sine of t, which is a pretty easy thing to memorize. Okay, so what I'd like to compute is I'd like to compute e to the I alpha plus beta, which I know is equal to e to the I alpha times e to the I beta. I know these things are true by the Taylor series examination of this stuff. Okay? So this is, I'm going off on a tangent right now to explain to you the angle formulas, and then we'll use them to rewrite this general solution. Okay, what's this left-hand side by Euler's equation?
The cosine of alpha plus beta plus I sine of alpha plus beta.
Very good. This left-hand side is going to be equal to, well, cosine of alpha plus I sine of alpha times cosine of beta plus I sine of beta. Right? I've just used Euler's formula everywhere. Now, I know that these two things are equal, and if two complex numbers are equal, what does that mean about their complex and real parts, or their imaginary and real parts?
They must be equal.
Yeah, the real part of this must be equal to the real part of this, and the imaginary part of this must be equal to the imaginary part of this. So all we need to do is find out how to express this in terms of real and imaginary parts, which is just foiling. So this is cosine of alpha, cosine of beta. And then I'm going to multiply the two imaginary components. I times I is -1, so I get minus sine of alpha, sine of beta. That's the real part of this complex number. Plus I times, and now I do the cross terms, sine of alpha, cosine of beta, plus this cross term, cosine of alpha, sine of beta. Now, by the fact that complex numbers are equal if and only if their real parts are equal and their complex parts are equal, we immediately produce our angle formulas. Cosine of alpha plus beta is equal to cosine of alpha cosine of beta minus sine alpha sine beta, and sine of alpha plus beta is equal to sine of alpha cosine beta plus cosine of alpha sine beta. And from this, you can derive all of the angle formulas that you want. You can derive the double angle formula by setting alpha equal to beta. You can write out triple angle formulas by just doing I alpha plus beta plus gamma is equal to e to the I alpha times e to the I beta times e to the I gamma. All of those complicated formulas that you were forced to remember at some point are all very simple consequences of Euler's formula. That's how you should think about it, and so you should never memorize those formulas again. You should just memorize Euler's formula. So I hope that's satisfying in some way, even if it's not the topic of this class. Any questions about how I derive these formulas?
No, that makes sense.
Yeah, excellent. So what I want to do is I want to rewrite this equation in a different way. And what I really want is I want one trig function. Here I've got two trig functions appearing, cosine and sine, but I want one trig function to appear, and this equation offers me the way to do it. So I'll write this side by side. What I've got is A, cosine of omega naught t, plus B, sine of omega naught t. And then separately, I've also got this equation. Cosine of alpha plus beta is equal to cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. What I'm going to do next is I'm going to do just a little bit of algebraic manipulation here. Notice that this is the same thing. Well, let me actually write it in terms of, this is fine. I'm going to do an algebraic manipulation here, and I'm going to change the alpha to a delta, just so that things look more like what we'll use. This also says that cosine of, what do I want to do? Yeah, I'm going to do cosine of negative delta plus beta. Just following the formula, this is the same thing as cosine of negative delta cosine of beta minus sine of negative delta sine of beta. But I can simplify these negatives, right? What's the cosine of a negative number?
It's just cosine.
Yeah, so this part is just equal to cosine of delta cosine of beta. What can I do with negatives and sines?
Sine of negative would just be negative sine, so the negatives are going to cancel.
Exactly. The negatives are going to cancel, so I'm going to get plus sine of delta sine of beta. Okay, so this is something we can use. Cosine of negative delta plus beta is equal to cosine of delta cosine of beta plus sine of delta sine of beta. Are we okay with this trigonometric identity?
Yeah.
Great. So what we would like to do for our change of coordinates is we would like to write A. Remember, A is some number, any real number in front of this solution. I want to write A as being equal to R times cosine of delta. And I want to write B as being equal to R sine of delta. If I am able to do this, if I'm able to find some real number R and some angle delta such that simultaneously A is equal to R cosine delta and B is equal to R sine delta, then this whole expression will become R cosine of delta cosine of omega naught t, and this part will become plus R sine of delta sine of omega naught t. What does our trig rule tell us that this equation would be equal to?
R cosine of negative delta plus sine of W naught t.
Yep. Okay, so I want to take a second and point out that we've done a really interesting change of coordinates here. Here, you're expecting a family of two variables, or a two-dimensional family of solutions. And here it's kind of very obvious and clear that you can mess around with A to be whatever you want, you can mess around with B to be whatever you want, and you'll get a two-dimensional family. Here, I also have a two-dimensional family, but my parameters are appearing in a very different way. My delta is some parameter on the inside of the cosine, and so if I change around with this delta, what that's doing is that's shifting the cosine function to the left or the right? And then R is controlling the magnitude of the cosine function. And moreover, what this tells us is this strange looking function, cosine, some constant times cosine of something plus some constant times sine of something, can actually be written as a single trigonometric function. Here you might have expected that there could be extra wiggles or something, like it's not exactly clear what sines plus cosines ought to look like. Here this is telling you it actually just looks like a cosine function that is shifted and scaled. So this already tells us something really interesting about all these functions. All of these functions are actually shifted and scaled cosines with a particular period. Okay. Before I go further, I want to ask, can I always find R and delta such that A is equal to R cosine of delta and B is equal to R sine of delta? Right, because this whole method depends on me being able to do this.
Yeah, you can.
Yes, I can. And why is that?
I'm not sure.
Yes, I can. This is essentially polar coordinates. That is, if I view, right, so for any fixed A and B are just two numbers. And so I can make a tuple and put it in the plane with coordinates a comma b, right? And now all I'm asking is, can I find r and delta such that I can write a and b in terms of r and delta? And the answer is yes. Just look at how you would write the point a and b in polar coordinates. You're going to find some delta, and you're going to find some radius such that a comma b is radius this many steps out at angle delta. And then just by our regular trig functions, we see that a is going to be equal to r cosine of delta, and b is going to be equal to r sine of delta. It's just polar coordinate expression of the plane. Kind of cool, huh? So this change of coordinates that we've done is kind of more serious than the other change of coordinates that we've done when we were, right? Like all the time that we discussed two-dimensional families, we saw that the Wronskian has like several different ways that you can think about it. But here what we've done is we've changed coordinates from Cartesian to polar and then seen what effect that has on our general family of solutions. And it turns out that the change of coordinates from Cartesian to polar enabled us to write this family in this way, which is very helpful for physicists because all of these constants now have very immediate physical meaning. Let's kind of take a look at this. So what happens when I plug in t is equal to 0 here? What's the value of the function for this solution?
R cosine negative delta.
Yeah, r cosine of negative delta, which is the same thing as r cosine of delta. So immediately we see that the magnitude of the function at time t is equal to 0 is exactly equal to r cosine of delta. And then it's going to be some cosine function, so I'm going to draw it something like this. Moreover, we know exactly what the, oh no, I don't have very many more pens. We know exactly what the amplitude of this cosine function is. What's this height?
R.
Yeah, it's just r. So immediately from this data, you can extract, you know that the solutions are cosine functions, you know that their magnitude is r, and you know that at time t is equal to 0, they start off at height r cosine of delta. What happens if we have a particular solution where delta is equal to 0?
Starts off at R.
Yeah, if delta is equal to 0, then this is just a scaled cosine function, r, something like this, where you start off at the top of the cosine function. So for this reason, delta has a name, and this name is the phase. So playing around with delta is just playing around with shifting your solution to the left or to the right, and having a delta of 0 or having phase 0 means that you're literally a cosine function and that you start off at the maximum amplitude. Okay. And of course, the period of this is going to be 2 pi over omega naught. So this distance right here is 2 pi over omega naught. Yeah. So I suppose there are a couple ways to think about this, but what I would essentially say is that even though we felt very happy with ourselves for finding a general solution that looks like this, a cosine of omega t plus b sine of omega t, kind of, if you're a mathematician, then you're done. You say, I have found all the possible solutions. There's nothing more for me to do with this problem. I'm done, right? What more can you ask of me? But we see that when we perform this change of coordinates, the equation that results is very nice if you want to actually understand solutions in a physical way or in a kind of a concrete application way. And there should be nice coordinates such that all of the parameters that are involved are telling you something concrete about the functions, right? Here, all of the parameters that appear, r, omega, and delta, are telling us very concrete things about how this cosine function looks.
Does it work out this nicely if you have the non-homogeneous equation where you have external forces?
No. Nope. The moment that you have external forces, we already know that this function is going to be modified, right? So this is the general solution, but I'm going to have to add some y in here. And the change of coordinates that we perform that makes this piece nice might do terrible, terrible things to our function y. So the moment that you add in a forcing term, things can get pretty much arbitrarily complicated, or a forcing or a damping term. Now, there are some functions, y, that behave nicely under this change of coordinates, and then those are functions that are nice to examine or look at from the physics perspective. Good question. Any other questions? No?
Nope, all good.
Okay. So you can kind of see maybe why I said you shouldn't study 3.7 too much. On one hand, what we're doing is interesting, but on the other hand, we haven't done any new differential equations. The differential equation was one that we were able to solve last week, and we haven't really done anything different in terms of solutions. We've just been able to write it in a convenient way where some of the details of how this function behaves are more exposed. Okay, let's do an example. So here is some physics problem. It's also worked out directly in the book. So first of all, as an example, let's suppose a 10-pound mass. Well, 10 pound is really a weight, I believe, but 10-pound mass stretches a spring by 2 inches. We're going to displace the mass by 2 inches from this resting displacement. And then we release with velocity 1 foot per second. Let's find the equation of motion. Okay, so the first thing that we want to kind of suss out here is what is the literal IVP that's being asked of us here. So let me draw a picture. Here is the spring with no mass, and it has length little l. Here is the spring with a mass at rest. So this length, L, is equal to little l plus 2. And then the problem says we take this system, which is currently in equilibrium and not moving, and we pull the mass even further so that the length is now the resting length capital L plus 2. So in other words, mu of t is equal to plus 2. Or mu of t0, not mu, u. U of t0 is equal to 2. Right? We've displaced this mass spring system by 2 more inches from the resting state of the mass spring system. So this is giving us one part of our IVP. What's the second part of our IVP?
Mu prime of t0 would be 1 foot per second.
Yes. Well, -1 because it's in the other direction, but yes. Also, we'll say it's times 0, so u of 0 is equal to 2. And then the other piece of data is it's being released with a velocity of 1 foot per second. So u prime of 0 is equal to -1 because it's going to have a 1 foot per second velocity going up.
Should we use inches or?
Yeah, we're using inches here, which is heinous, but okay. So in this case, yeah, you're right. U is going to actually be 1/6, 1/6 of a foot. Yeah, so we should use feet instead of inches, I suppose, just to be compatible with the problem. So we're being displaced by 1/6 of a foot, and our velocity is 1 foot per second. The next thing that we need is we need to find the spring constant. So how do we find the spring constant? Do we have any nice equation that involves just the pieces that we know?
Hooke's law.
Hooke's law. So Hooke's law states that the force of the spring is equal to the length times some constant k. So that does give us part of it. Yes.
Is it the mg minus kl equals 0?
Yeah, I agree. So how to find k? We should examine the equilibrium solution. Namely, if we look over here, where nothing is moving, our free body diagram looks like this. We've got mg, the force of gravity pulling us down, and we've got kl, the force of the spring pulling us back up, and we know that mg plus negative kl is going to be equal to 0, because since this thing is at rest, it has no velocity, so no acceleration. And we already know what mg is. So mg is just going to be the weight, namely 10 pounds. So 10 plus negative k times the length, the rest length, which is 2 inches from the little l, is equal to 0. So k should be equal to 60.
I have a question.
Mm-hmm.
Do we not have to multiply the mass by gravity, or is that because we're talking about weight right now and not exact?
Yeah. So when I say 10 pounds, that is the same thing as saying this is equal to mass times gravity. And so if we want to find the mass, we need to do the following calculation. So the mass is going to be equal to weight over gravity. and the gravitational constant written in feet is 32. So the m is going to be 10 over 32.
Okay, thank you.
Yep. And so now we have all of the constants that we need to write out our actual equation of motion. So we assume no damping and no forcing. So what is our actual differential equation that must be satisfied? Well, remember that it's m u double prime being equal to mg minus ku t. And we know what all of the m's and g's and things like that are here, right?
Doesn't the mg go away when we have the mg?
Oh, yes, yes, you're right. Yes, you're right. So this is mg minus k times L plus u of t. But of course, the mg minus kl will be 0. And so I'm just left with mu double prime is equal to negative ku of t. What is m?
10 over 32.
Yep. 10 over 32 times u double prime plus 60u is equal to 0. And the IVP, the associated initial data that we need, is exactly what we found up here. U of 0 is equal to 1/6, and u prime of 0 is equal to negative 1. And we could probably rewrite this nicely by multiplying by 32 over 10. So we'd get u double prime plus 32 times 6u being equal to 0, which is equal to u double prime plus 192 u is equal to 0. So what I would like for you to do is, using this problem and this initial data, which we had to do some work in order to find all these coefficients from what the problem gave us. But once we're here, could you write out the equation of motion in terms of r cosine of omega 0 t minus delta? And you don't have to be explicit about, you don't have to find actual numbers for r and delta, but if you can write it as an inverse trig function, that'd be sufficient. So write, oh, sorry, in this form. So give this a shot for a minute or two. I'll be right back. So I think that the best thing to do first is to find this explicitly in terms of A cosine of omega naught t plus B sine of omega naught t. Does anyone have the roots of the characteristic polynomial for this?
Is it just plus or minus I root 192?
Yeah, exactly. Plus or minus I root 192. So we know that the general form of this differential equation is A cosine of root 192 times t plus B sine of root 192 times t. And then what do A and B have to be?
R cosine delta and R sine of delta.
So that's correct, but we don't know what delta is yet. So I think it's easier to find A and B first in this form, and then make the change of coordinates afterwards. In particular, here what we need to do is plug in our initial data. It's easier for me to compute derivatives with these things than it is for me to compute derivatives with this thing, just by a little bit. So what is, if I plug in 0 for this equation, so y is equal to this, y of 0 is equal to just from this. If I plug in 0, what do I get?
Is it A is equal to 1/6?
Exactly. Y of 0, if I just plug in 0 here, this whole term goes to 0. This term goes to cosine of 0, which is 1, and I get A. So A must be equal to 1/6. Similarly, I need to take the derivative of this function and evaluate it at 0. So the derivative of this function is going to be y prime of t is equal to root 192a negative sine of 1 root 192t. Then the derivative here is going to be plus root 192b cosine of root 192t. And what happens when I plug t is equal to 0 into this equation?
The sine term drops out.
The whole sine term is going to drop out, and the cosine term is just going to be equal to 1. So I get y prime of 0 is equal to root 192b, but I also, by the initial data, demand that it's equal to -1. So this has to be equal to -1, and we get that b is equal to -1 over root 192. This okay?
Yeah, that makes sense.
So as far as we're concerned, in terms of the previous sections, then our genuine equation of motion is y of t is equal to 1/6 cosine of root 192 t minus 1 over root 192 sine of root 192 t. And then if I want to change this equation into the physicist's parametrization of this family, then all I need to do is I need to plot 1/6 and 1 over root 192. So 1/6 and negative root 192, and compute what's going on here. Right, so here I could make a triangle like this. I could find this angle, and here I'm going to have 1/6 being whatever our formula is, and the other one over here. I don't want to redo all the trig, but I'm just showing you exactly how you would calculate this stuff if you had access to a calculator. You'd just be doing inverse trig functions of some stuff. In particular, it's easy to find R, right? What's R? How do I find the length of a hypotenuse?
I got 13.86.
Oh, I did not know y'all were going to actually calculate. I was just going to say it's the square root of 1/6 squared plus negative root 192 squared. Just the Pythagorean theorem. If you actually calculated it, that's great. But I'm just saying you are all very familiar with the methods of passing in between the family written like this, or the specific equation written like this, and finding R and delta such that you can rewrite it in the form, whatever this is, 1/6 squared plus root 192 squared times cosine of delta, which you find using tangent, right? You could probably find delta as the arctangent of negative 192 over 1/6 or something. Anyways, I don't want to continue on too much further because I think y'all get the point, and I haven't really done any new differential equations here. I've just kind of gone through a specific problem where we can find the equation of motion very concretely. Any questions? No? Okay. So now, in the remaining 25 minutes that I have left, I would like to discuss higher order linear differential equations. So this is our brief stint in chapter 4, which will be today and Monday. And hopefully what you find is that nothing is surprising. Higher order linear differential equations. Are we ready to move on, by the way? I know that I've turned the page and started writing, but does anyone want to ask a question about the material that we did in chapter 3 or the material we did today or anything like that?
I'm good to move on if everyone else is.
Great. Okay. Can someone give me the general form for an order n linear differential equation? Order n linear differential. What does the order n mean?
The highest derivative is the nth derivative.
Right. So I've got to have a d to the n y over dt to the n. And what sort of coefficient can I have in front of this?
Some function of t.
Right, some function of t. So I'll call it Pn of t plus Pn minus 1 of t, some other function of t times the n minus first derivative, which I'll use in this parenthetical notation. N minus first derivative, maybe I should write parentheses around here, although it'll get annoying. Hopefully you won't be confused by what I write. N minus first derivative of y with respect to t, all the way down to the p first derivative of t, or sorry, some function p1 of t times the first derivative with respect to t, or I should write dy over dt plus p0 times y being equal to g of t. Right? This is not unexpected at all. This is exactly what we expect from an nth order linear non-homogeneous differential equation. And of course, we can divide by p to the n of t. And so we get something that looks like L of phi. We can once again use the linear operator terminology. L of phi should be equal to d to the n over d to the n of phi, plus, now I'll write with lowercase p to the n minus 1 times d to the n minus 1 over dt to the n of phi, plus all the way down to p0 of t times phi being equal to g of t. Here, this is not the same g of t up here. It's g divided by pn of t. So this is not in the least surprising. Okay, what do we expect from general solutions? How about what should an IVP look like? Anyone have a guess? For instance, how many parameters should be involved with our general solution for an nth order linear differential equation?
N minus 1. Or n, actually.
Yeah, I think we should expect n. Should expect an n parameter family of solutions. And what about IVPs? How much data should you have to specify in order to specify a unique solution?
Data for all of the y's up to the n minus 1 derivative.
Yeah, we should expect up to n minus 1 derivatives of data. So we want y of t0 is equal to y0. We want y prime of t0 to be equal to y0 prime. This is the amount that we got for second order, right? Here is all we needed for an IVP for first order. Here's all we needed for an IVP for second order linear. And then all the way down to y to the n minus 1 of t0 should be equal to y0 n minus 1. So this should be the amount of initial data to determine a unique solution. Right? We can start writing down the existence and uniqueness theorems. And I'm sure that you'll be able to guess the content of the existence and uniqueness theorems. So once again, as has been my habit, since we move from first order to second order, I won't be proving this because it requires more analysis than we have. But I can at least state the existence and uniqueness theorem. But does anyone have a guess about what my existence and uniqueness theorem should be based on this?
You'll have an interval where y is continuous wherever all of the functions of t are continuous.
Exactly. I should just demand that all of the functions of t ought to be continuous, and then I will have existence and uniqueness for IVPs on intervals where all those functions are continuous. And that's exactly what happens. So you see the behavior of linear differential equations continues to be as nice as we could possibly desire And it's really the non-linearity that immediately throws our hopes out the window, so to speak. So if Pn minus 1 of t all the way down to P0 of t and g of t are continuous on an interval I, then there exists exactly one solution, y is equal to phi of t, solving an IVP with the data y0, y prime of 0, all the way down to y to the n minus 1 for its derivative, evaluated at t0, where t0 is inside the interval. Moreover, a solution exists on I. So I'm writing slightly different words, but this is exactly the same kind of result that we had in both the first order linear and the second order linear. First of all you need to check are where the coefficient functions are continuous. You find the biggest interval on which all of these functions are continuous. And then if you have initial data t0 inside that interval, you have existence and uniqueness of solutions, and your solution is defined on that whole interval I, where all of these functions remain continuous. Any questions here? Right, so you see what I mean when I say really none of this is surprising. All the behavior we've already kind of seen in the second order case. Okay. Oh, yeah, question?
Sorry, no, I was agreeing with you.
Okay, great. So again, the easiest case for us to actually analyze will be starting with the homogeneous part. So again, let's begin with the homogeneous piece. Which is precisely the condition that L of phi is equal to 0, where now L is the differential operator represented by d to the n, d over t n, plus some polynomial in t times d to the n minus 1 over dt n minus 1 all the way down to here, right? Homogeneous just means that this stuff in terms of g is 0. Nothing unexpected here. What do I want to say? So we want or expect a general solution which is of the form y1 all the way up to yn, where each of these are solutions. And we want to think of what it means to be a fundamental system of solutions. So what does it mean? So assume that we have solutions, so particular solutions, y1 all the way up to yn, such that L of yi is equal to 0. Right? This is just exactly what it means for these to be solutions to the homogeneous part of the differential equation. So what do we need to check? In order for us to be able to write any solution or write the solution to a specific IVP in terms of linear combinations of the yi.
Linear independence.
Yeah, exactly. I need some condition on not only these functions, but on all their derivatives, right? Like, literally, what does it mean to write a given solution to an IVP in terms of these functions? It means if we're given initial data, y naught prime, all the way up to y naught n minus 1, then what we're asking for is, do there exist constants k1 all the way up to kn, such that, well, first of all, k1 of y1 at t0 all the way up to kn times yn at t0, what does this have to be equal to?
0.
Well, technically it has to be equal to y0, our initial data, right?
Yes.
Right. I'm really asking, when is this equal to y0? And I'm also asking, when is k1 y1 prime at t0 plus kn yn prime at t0, when is this equal to y0 prime, all the way down to when is k1 y1 to the n minus first derivative at t0 plus kn yn to the n minus first derivative at t0, when is this equal to y0 to the n minus first derivative, right? Do you agree that I can write any IVP, that is, any differential equation which solves the differential equation and also satisfies the IVP in terms of these functions? Like, do you agree that this condition that I'm writing here, having some constants k1 through kn, such that all of these equations hold, is equivalent to writing the unique solution to L and this initial data in terms of my functions y1 through yn? Yes or no?
I guess I don't totally understand what you're saying.
Right. Okay. So what I'm saying is the following. Let's take the following. Let's take L, an order n differential equation, linear homogeneous differential equation, and some initial data, y0, y0 prime, all the way up to y0 n minus 1. You agree that this is the correct amount of data for an IVP for an order n linear differential equation?
Yes.
So by the theorem, by existence and uniqueness, there exists a unique solution to this IVP. Namely, there's some function y such that L of y is equal to 0, and y of t0 is equal to y0, et cetera, et cetera, et cetera, right? So we know that some function y exists which satisfies this IVP by the existence and uniqueness theorem. We're okay with this?
Yeah.
So now the question becomes, let's say separately from all this, I have somehow managed to find n solutions to this differential equation, namely L of yi is equal to 0. my question is, can I write this y in terms of a linear combination of these yi's? Can I write this y in terms of these ones? I can't fit them both on the page, but right. And all that I really need to show is that by existence and uniqueness, if I can find a linear combination of these yi's that satisfy all of these initial conditions, the uniqueness part means that y would be forced to be equal to k1 y1 plus kn yn. Right? I'm guaranteed that y can be written in this form if I can force some linear combination to satisfy all the initial data by the uniqueness part of the existence and uniqueness.
Okay.
Is that a little better?
Yeah, thank you.
And this is just me saying, well, if I have some function which is a linear combination of these and has to satisfy this initial data, I set it equal to y0. If the derivative of this function has to be y0 prime, well, this is just the derivative of the function. I took the derivative of all the y pieces, and I demand that it's equal to y0 prime. And the nth derivative of this function, which is this, I demand that it's equal to y0 n minus 1. So, right. And now this immediately brings us to the notion of a Wronskian, which is essentially a form of checking linear independence for this set of functions, y1 through yn. So this system of equations on the previous page, that big system of equations, has a solution. In particular, if w of y1 all the way up through yn of t0 is not equal to 0. Or in other words, here, what I should really be thinking about is I take this system of equations, k1, kn, all of these things, and then my question is the determinant of y1, y1 prime, all the way up to y1 to the n minus 1 derivatives, y2, y2 prime, all the way up to y2 to the n minus 1 derivatives, y3, y3 prime, all the way up to the y3 n minus 1 derivatives, all the way out to yn prime, down to the yn minus first derivatives of n. I need to ask whether this determinant is non-zero.
Yikes.
Right, exactly. So you can immediately see that very quickly the computations of this sort of thing become unmanageable, right? You can do 3x3 determinants, and maybe you can do a couple 4x4 determinants, but if these are a whole bunch of different functions and you're being asked to compute a huge determinant, it's pretty difficult to do that by hand. But nonetheless, this is a concrete condition that you can think about, right? If this determinant is non-zero, that's equivalent to saying that you can find constants k1 through kn such that when you apply this matrix to k1 through kn, they'll be equal to that vector of initial conditions, namely y1, y1 prime, all the way down to y, like the nth derivative of y. Okay, so maybe I should just stop here, but I hope that you see that on one hand, sure, the matrices are getting bigger, but all of this is exactly what you would have expected from the second order case. First of all, you expect families of the same number of parameters, namely you expect n parameter families for your solutions. For the IVPs, you know how much data to ask. You ask for the value of a function all the way up to the n minus first derivative of the function at some t0. And then, furthermore, we're going to see that we can get a fundamental system of solutions, y1 through yn, and we can check whether that system is a fundamental system based on the determinant of the Wronskian, or based on the Wronskian, which is the determinant of this matrix. Any questions on this? I hope this doesn't feel like too much of a jump. I mean, on one hand, the notation is getting more complicated because I'm suddenly dealing with a lot more functions, but like in terms of the ideas, I haven't actually introduced any new idea. Just thinking about linear independence of a family of functions. Okay, that'll be all for today. And I'd be happy to, yeah, have a nice weekend. Stay safe this weekend, please. Take care of yourselves. And I'll see you on Monday.
Thank you.
Thank you.
Of course. Oh, if we planned on meeting today during office hours or something like that, could you send me a message just privately in a Zoom chat so I can kind of remember what to expect? That'd be great. All right, I'll be back at like 1:05.